Lighthouse Scientific Education presents a lecture in the Chemical Reaction Series. The topic, Net Ionic Equations. Part 1. Part 2 is in the Solution Series and uses the solubility rules. Not all students will study this topic to that depth. Know what is expected of you. Material in this lecture relies on an understanding of the previous lectures, ionic bonding, and balancing chemical equations. The lecture begins with some definitions, including chemical equation, total ionic equation, net ionic equation, and spectator ions. Then it is on to the steps for producing net ionic equations, with 3 example problems that highlight some of the issues that come up with net ionic equations. Definitions. First up is the chemical equation, and this definition is in the context of net ionic equations. Such chemical equations may be given with balanced coefficients or have balancing as a step prior to the process of getting net ionic equations. At this point, all ionic compounds are shown as neutral compounds. Below is an acid-base reaction written as a chemical equation. Note the AQ subscript. As a refresher, AQ is the phase description that stands for aqueous or dissolved in water. Another more useful term associated with AQ subscript is dissociates. That indicates that the cations and anions are separated from each other and found in solution surrounded by water molecules. In this reaction, both KOH and HNO3 are dissolved in water. KOH is an ionic compound that dissolves or dissociates into its constituent ions. HNO3 is an ionic compound that dissolves or dissociates into its constituent ions. Another way of saying this is that KOH and HNO3 are soluble, which follows from the definition of solubility. It is the ability of a substance to dissolve in a solvent. For net ionic equations, that solvent will be water. So the term soluble means able to dissolve in water, and insoluble means unable to dissolve in water. Solubility is a topic for the solution lecture in the solution series of lectures. The definition of total ionic equation is the balanced chemical equation in which ionic compounds are shown in their predominant aqueous form. The KOH in the chemical equation is shown as the potassium cation and the hydroxide anion, since this is how KOH is found in water. It is a strong base. The AQ subscript is necessary here since ions do not exist for any length of time outside of their solvent. Importantly, all of the compounds with the AQ subscript are written as ions in the total ionic equation. The nitric acid and the salt potassium nitrate are also shown in their predominant aqueous form. It is the AQ subscript that is the indicator to break the ionic compounds into their constituent ions. In the second lecture on net ionic equations, a set of rules is offered that can also be used in determining soluble ionic compounds. The last definition and the topic of this lecture is the net ionic equation. It is the balanced chemical equation that only shows species that participate in the reaction. It is the total ionic equation that omits or ignores spectator ions. And just what are spectator ions? They are ions that remain unchanged in a reaction. They do not participate in the reaction. They are there, but do not react. Referring back to the total ionic equation, we see that the potassium ion is on the reactant side and the product side. It is unchanged in the reaction. The same can be said of the nitrate ion. It too is unchanged. These ions are spectators or onlookers to the reaction. Not including them in the net or remaining ionic equation leaves just the reactants that participate in the reaction and the products that they form. The net ionic equation just shows the actual reaction, A quick note on the products found in a net ionic equation. They need to be stable molecules or compounds. They can be a gas or a liquid or a solid. What they cannot be is a soluble ionic compound. KNO3 is not a product in the net ionic equation because it does not form a stable compound. The potassium and the nitrate most certainly need to be in the reaction because a hydrogen ion or a hydroxide ion cannot be added by itself. Ions are added as neutral compounds. So, why spend the time and energy getting a net ionic equation? By comparing the net ionic equation to either the chemical equation or the total ionic equation, we can see its attraction. The net ionic equation just shows the relevant parts of the reaction, which makes it easier to follow. Simplicity is its goal. Getting a net ionic equation from a chemical equation really just follows from the definitions listed here. Net ionic equations are usually just limited to reactions that take place in water and have soluble ionic compounds. Be sure that that is the case before proceeding. The first step in getting a net ionic equation is to write out the balanced chemical equation. Write out the reactants and products. Be sure to include the subscripts of state of matter, especially the aqueous subscript. Then, rewrite the chemical equation using ions for compounds listed as aqueous. Essentially, write out the total ionic equation. It should be pointed out here that this step is modified in the more advanced net ionic equation Part 2 lecture. In that lecture, the student is responsible for determining which compounds are soluble. They do not rely on the AQ subscript. To dramatically simplify the process, a table of solubility rules is provided. If the student's coursework regarding net ionic equations involve using these rules, then follow this lecture up with the Part 2 lecture. If not, then continue on. And that involves noting in the total ionic equation which ions participate in the reaction and which are spectator ions. That allows for step 3. Rewrite the total ionic equation without spectator ions. Finally, double check that the equation is still balanced. Also, double check that the total charge is balanced too. A balanced charge is one in which the total charges on the reactant is equal to the total charges on the products. The charge contribution of an ion is found by multiplying its charge by its coefficient. On to some practice problems. The process begins by writing out the chemical equation with its states and phase subscripts. Problem 1 has aqueous silver nitrate reacting with aqueous potassium chloride to produce solid silver nitrate and aqueous potassium nitrate. A question to always ask when dealing with chemical equations is whether or not the equation is balanced. It cannot be assumed that every equation handed to a student is balanced. In fact, if there are no coefficients attached to the equation, then that is a red flag for a potentially unbalanced equation. Inspection of this equation shows each element, ion and polyatomic ion, coming up once as a reactant and once as a product. The equation is balanced. That allows us to rewrite the chemical equation using ions for compounds listed as aqueous. Write a total ionic equation. The first reactant in the chemical equation is AgNO3, and it dissociates in water as indicated by the AQ subscript. The total ionic equation will therefore write the compound as dissolved ions, Ag plus and NO3 minus. Aqueous subscripts are included. The KCl is also in the aqueous phase, so it is written as dissolved K plus and Cl minus. Aqueous subscripts are included. That is the reactant side. For the products, AgCl is a solid. It is placed in the total ionic equation unchanged. That is not the case for the other product, KNO3. It is in the aqueous phase and written as the dissociated K+ ion and the negative nitrate ion. Aqueous subscripts are included. The total ionic equation is complete. While we have it here, we should note which ions participate in the reaction and which ones are spectator ions. A good place to start is to look at the formed product. The solid AgCl tells us that the silver ion in the reactant is a participating ion, as is the chloride ion. These ions react to form AgCl. What about the spectator ions? Are there ions that remain unchanged in this reaction? Yes. The nitrate is found as a dissolved ion on the reactant and product sides. So is the potassium ion. We are now ready for the third type of equation, the net ionic equation. We will take the total ionic equation and rewrite it without the spectator ions. In other words, remove the nitrate ion from both sides and remove the potassium ion from both sides, leaving the reaction aqueous silver ion plus aqueous chloride ion react to form solid silver chloride. The reaction has been reduced to its essentials. Is this equation balanced? There is one silver and one chloride on each side, so yes. If the answer is no, then return to the chemical equation and verify that it is balanced. What about charge? Is the total charge on the reactant side equal to the total charge on the product side? Silver chloride is a neutral compound, so its net charge is 0. On the reactant side, there is a single positive charge and a single negative charge, which combine for a net charge of 0. Yes, charges are balanced, and the equation checks out. The problem is complete. The second practice problem begins the same way. Write out the balanced chemical equation. Be sure to include the subscript state of matter, especially the aqueous subscript. That chemical equation is aqueous barium chloride reacting with aqueous sodium sulfate to produce solid barium sulfate and aqueous sodium chloride. Is the equation balanced? The lack of coefficients means we should check. Since this is not a lecture on balancing chemical equations, we will cut to the chase and add a 2 in front of the sodium chloride. Now, that is a balanced equation. Proceed to step 2 and rewrite the chemical equation using ions for compounds listed as aqueous. Write the total ionic equation. Starting with the first reactant, aqueous barium chloride, BaCl2. It is an ionic compound that dissociates in water and is written as an aqueous Ba2+ ion and 2 aqueous Cl- ions. Problem 2 brings in a new element in that there are compounds that have multiple anions or cations. There is only one barium chloride compound in this reaction, but it has 2 chloride ions, and the total ionic equation needs to reflect that ratio. It does so by taking the 2 subscript and putting it as a 2 coefficient. This same feature can be seen with the aqueous sodium sulfate. As a dissolved ionic compound, it is found in the total ionic equation as 2 dissolved sodium ions and 1 sulfate ion. Again, the 2 coefficient in front of the sodium comes from the 2 subscript in the sodium sulfate. Now, to the products. Barium sulfate is a solid and remains unchanged in the total ionic equation. The other product, aqueous sodium chloride, is a dissolved ionic compound and written in the total ionic equation as 2 solvated sodium ions and 2 solvated chloride ions. The second new element in this problem is the presence of a non-1 coefficient in front of a compound. The total ionic equation is a balanced equation. That 2 in front of the sodium chloride has to be included in the total ionic equation. There are 2 sodium ions in 2 sodium chlorides. there are 2 chloride ions in 2 sodium chlorides. So, when including a dissolved ion in the ionic equation, it must be given a coefficient that represents both the coefficient and subscript of that ion when written in the compound form. To further clarify this statement, consider a situation in which the aqueous sodium sulfate had a coefficient of 3 in a balanced chemical equation. Not this equation, but a hypothetical reaction. In writing this compound as an ion in a total ionic equation, what coefficient would the sodium ion receive? There are 3 sodium sulfates, and each one has 2 sodium ions. The way to get the value is to take the coefficient of the compound, 3, multiply it by the subscript on the sodium. The correct coefficient for the sodium ion is 6. Using the same equation for sulfate, coefficient of 3 times the implied subscript of 1 gives 3 sulfates. Be sure not to confuse the subscript 4 on the oxygen of the sulfate as a subscript in this math. There is only 1 sulfate polyatomic ion in the sodium sulfate compound. Back to the problem. And it's time to identify which ions participate in the reaction and which ones are spectators. Taking the product, solid barium sulfate, as a guide, the reactant barium ion and the reactant sulfate ion are both required for this reaction. Ions found unchanged on both sides of the reaction include the chloride ion and the sodium ion. The third equation, the Net Ionic Equation, is a rewrite of the total ionic equation without the spectator ions. The chloride ions are removed, as are the sodium ions. What remains is the Net Ionic Equation. Aqueous barium ion reacts with aqueous sulfate ion to form solid barium sulfate. Sweet and simple. Is this reaction balanced? Well, there's 1 barium and 1 sulfate on the reactant side and 1 barium and 1 sulfate on the product side. It is balanced. What about charge? The product, barium sulfate, is a neutral compound, so its net charge is 0. On the reactant side, the barium has a +2 charge, which is matched by the -2 charge on the sulfate. Both sides of the reaction have a net charge of 0. The charges are balanced. Our final practice problem has us write out the balanced equation with phase and state subscripts. Solid magnesium reacts with aqueous hydrochloric acid to produce aqueous magnesium chloride and hydrogen gas. Is the equation balanced? Well, there are 2 hydrogens on the product side, but 1 on the reactant side. So, no, it isn't. Adding a 2 to the HCl takes care of business, and it is on to step 2, which has us rewrite the chemical equation using ions from compounds listed as aqueous. Write the total ionic equation. The first reactant is the solid magnesium. This goes unchanged in the total ionic equation. Not so for the aqueous HCl. It is found as dissociated ions in solution and is added to the equation as 2 H+ and 2 Cl- ions. Remember to include the coefficient in front of the compound. On the product side, there is the aqueous MgCl2. In the total ionic equation, these aqueous ions are written as Mg with a +2 charge and 2 Cl- ions. Be sure to incorporate the 2 subscript as a coefficient. The last compound is the hydrogen gas. It is not an ionic compound and is left unchanged. This brings us to a generalization. Solids and gases will be part of the Net Ionic Equation. And this brings us to the point where we identify ions that participate in the chemical reaction and those that do not. Unlike problems 1 and 2, this one doesn't have a solid as a product. It does, however, have a stable formed compound, hydrogen gas. This means that the hydrogen ion on the reactant side participates in the reaction. While the products do not contain a solid, the reactants do. Magnesium solid is transformed into magnesium ion. Going from an elemental form to an ionic form is a chemical reaction. The magnesium ion is a participant in this reaction. And that leads to another generalization. Look in the products for participating ions. Not all participating ions will be in the reactants. As for spectators, there is a chloride ion on the reactant side, and on the product side, it is unchanged and therefore denoted as spectator. With these two equations, we are ready to generate the net ionic equation by rewriting the total ionic equation without the spectator ions. The chloride ion is removed, giving a net ionic equation of solid magnesium, reacts with aqueous hydrogen ion, producing magnesium ion and hydrogen gas. This is a redox reaction in which electrons are transferred from the magnesium metal to the hydrogen ion. Is it balanced? Well, there is only one magnesium on both sides of the reaction. That there's been a loss of electrons does not mean that the atom in the reactant is not the ion in the products. There are 2 hydrogens on the reactant side and 2 on the product side. So yes, it's balanced. What about charge? Is the net charge on the reactants the same as the net charge on the products? On the reactant side, there are 2 +1 ions for a total charge of +2. On the product side, there is 1 ion with a +2 charge. Both sides have a total charge of +2 and are balanced. And that leads to our final generalization. Net ionic equations do not need to be neutral. They are not full equations and omit the charges on the spectator ions. Therefore, they can have reactants and products with charge as long as the total charge is balanced. Recapping the lecture. To get a net ionic equation, begin by writing out the balanced chemical equation. Chemical equations are balanced equations in which the ionic compounds are shown as whole compounds. Include state of matter and phase. Be sure to include the AQ if possible. Solubility was defined as the ability of a substance to dissolve in a solvent. This lecture dealt strictly with water as a solvent. Then rewrite the chemical equation using ions from the compounds listed as aqueous. Write the total ionic equation. That is defined as a balanced chemical equation in which ionic compounds are shown in their predominant aqueous form. If the compounds dissociate in water, write its ions as aqueous ions. Be sure to keep track of the coefficients and subscripts of the compounds so that dissolved ions come in the same ratio. With the total ionic equation, note which ions participate in reaction and which are spectator ions. Spectator ions are the ions that remain unchanged in a chemical reaction. These are dissociated ions that do not participate in the chemical reaction. They are unchanged in the reaction. Next, rewrite total ionic equation without spectator ions. The net ionic equation is the balanced chemical equation that only shows species that participate in the reaction. Finally, double check to see if the equation is still balanced. Also check to see that the reactants and products have the same net charge. And that concludes the lecture on net ionic equations. If your coursework has solubility rules attached to the net ionic equation, go to the follow-up lecture, Solubility Rules and Net Ionic Equation, Part 2. It is in the Water in Solution series.